Okay, now we continue to talk about the section 15.2, the orthogonality. So last time we followed the textbook and showed this relationship. So the product of two legitimate polynomials of order n and m and integrate from the whole range dx from -1 to 1, you get this constant 2 divided by 2n plus n times the Kronecker deltas. It means that for n not equals to m is 0, for n equals to m is 1, so the product is just 2 times 2 divided by 2 plus 2n plus 1. So now the textbook, the derivation is a little complicated. So there are actually other ways to do it. Your textbook also mentioned there will be an exercise in the end of chapter question to use another way to prove that. I think we'll use in that exercise we'll use the Rodriguez formula to find out this to derive this formula. But there are actually other ways to do it, and an easier way to do it is using one of these recurrence formula. Actually, more than one can be used, but I'll start with a recurrence formula. So that is in 15.22. So the recurrence formula is Pn plus 1 pi the derivative dx of dx dp dx and minus p pi n minus 1 x equals to 2n plus 1 times pn x. Okay, so I'll start with this recurrence formula because you already have this 2n plus 1 like this one, and then you have pn. All right, so what we can do it by straightforward. So we want to find out the case for n equals to m. So now we can multiply by pn to the left-hand side and the right-hand side and do the integration. So you can write like 2n plus 1 integrate pn square dx. So multiply pn and do integration. Now that equals to integrating. So there are two terms. So you have pn x times dpn plus 1 dx minus dp and minus 1 dx. Integrate over x. Okay. And now the first obvious integration is that the second term will be 0. This is because that's coming from the fact that legitimate polynomials are all orthogonal. So because this is p to the n minus 1 power, so the highest order, higher power in x of this p to the n minus 1 is x to the n minus 1 power. You need to do the derivative of x. So the highest order, higher power in x is x to the n minus 2, and then you multiply by pn. Okay, and do the integration. So you can figure that out, that any x to the power m pn dx will be 0 if m is less than n. Okay, because an xm would be can be expressed as a summation of legitimate polynomial up to p to the p sub m, and all the lower order. But then as long as m is less than n, all this integration will be 0 by the orthogonal condition. So this the second term will be obviously 0. This will be 0. Okay, so we only have the first term. And the first term, we can work out the first term by doing an integration by parts. So this is equals to Pn plus 1, evaluate at x from -1 to 1, and then minus integration of this one, Pn plus 1, times the derivative of dPn dx. Okay, now the second term, this one is 0, exactly the same reason that this term is 0, because this is Pn plus 1 times the derivative of Pn dx. Okay, so this one is also 0. Okay, now this one evaluate the two limits would be Pn 1, Pn plus 1 at 1, minus Pn minus 1, Pn plus 1 minus 1. Okay, now all the Legendre polynomials are defined with the value is 1 at x equals 1, so both of these and this is 1, so this is 1, so the whole thing is 1, so this one is 1. Okay, and this one, because they are off by a 1 in the order, so this is n plus 1, so one of them must be odd, the other must be even, and the Pn that's -1 is equals to -1 to the n power, so this is -1 to the 2n power 2n plus 1 power. Okay, and so this is odd, so you will get a negative sign, cancel with this negative sign, so this is also, so you subtract -1, so this is altogether is 2. Okay, so this means that this is equals to 2. This implied Pn square x dx equals to 2 divided by 2n plus 1. Okay, so this is exactly that one.